Alrighty. Oops, sorry. So we are kind of getting toward the end of chapter 2 here. So I think we'll be done with 2.7 today. And then we'll spend Wednesday and maybe part of Friday on 2.8. It won't take us a whole hour and a half on Friday, I'm saying on that. And then we'll be done with material for test 1. So let's see, where do we leave off? We talked about limits at infinity. That was the last thing we were doing in here. We finished off looking at a few examples, and the trickiest one, not the trickiest one, had one where if we thought about just plugging the number in, we got into an infinity minus infinity situation, and we said we can't subtract infinity from infinity. So I had to come up with some way of dealing with that, and the way we did it was to, in that case, we had a square root, so we rationalized. And we had some things cancel out. And we could get to our limit that way. What Friday seems like a long time ago. I don't feel like I had a long weekend though. I don't know how that works. I feel like the weekend's short, but it still seems a long time away. Okay. So today in 2.7, we're gonna eventually get to something we call a derivative. Okay. If you've seen calculus ideas before, you'll be familiar with that term. And then we're gonna talk about how that relates to things like slope of a tangent line and rates of change. This idea of a derivative. So first, let's just kind of think back to our motivation for this chapter. Back to our motivation for this chapter. We had a couple of problems we were thinking about. We had the tangent line to a curve at some point. And then we had the issue where we're trying to figure out velocity at a certain instance in time instead of average velocity. And we saw that those ideas were really similar, right? That we could take the velocity problem and really it turned into slope of a tangent line into a curve. So those two types of limits is what we're going to give the name derivative. And we're going to give those types of limits the name derivative. In this section, we're just really looking at interpretations. We're going to look at a few different situations, and we're going to have a few functions where we'll do the whole process and go through, find the derivative, and then find the slope of the tangent line, put all that together. And not a whole lot new in this section. That's good news. So let's start from the tangent line perspective. Tangent line to a curve. So we've already looked at this, a fair amount. So here we're thinking about we've got some curve, we're calling it C. You just think about f of x. And we want to find the tangent line to our curve at some point. Our point we're calling A f of A. So what we did is we picked out another point that was close to the point that we're concerned about. And then we find the slope of the secant line. So in this case, the way we have all that labeled around our point Q, our point that's close to point P, our y coordinate would be f of x, and then the y-coordinate of the point we care about, f of a. Then on the bottom, our x values, and we have x minus a. Same idea we've dealt with, maybe labeled slightly different. Slope of our secant line. And then we said we were going to let our nearby, our close point Q, get closer and closer and closer to P. So now that we have limits in our vocabulary, we can say we're going to let point Q approach P. Right, we're going to look at the limit. And we saw that as we do that, okay, the closer we get our point Q to our point P with our secant line, closer and closer and closer, the slope of that line is going to get to the slope of the tangent line. So now we actually have the tools we need, not only to get closer and closer and closer, but we can actually talk about the limit. We can talk about the limit as one point approaches the other. So if we do that, we're done if our 2 points are getting closer to each other. So A is the one that we care about. X is the one that we're picking to be close to the other point. So we would look at the limit as x approaches A, as the two values get really close together. And that gives us the slope of our tangent line. So we get that ratio and we take the limit, and as our denominator approaches 0 is another way of thinking about that. Get the slope of our tangent line through that limit. And nothing really new there, we're just kind of putting it all together in one slide. So let's kind of do an old problem. This is one like similar to what we've done in another section. So we've got parabola y equals x squared, and the point P, 1, 1. We want to find the equation of the tangent line. There you get a little preview, but let's go over to our scratch paper here. So here's what we're working with. We've got, I'm going to call it f of x instead of y. There's our curve, and we want the slope of the tangent line at the point P. Well, we want the equation of the tangent line first, we've got to have the slope. So our definition we just saw said the slope of our tangent line, I'm going to call it m tan. It's going to be the limit x approaches the x value of the point we want, which is 1. That was A in our formula as x approaches A. So then we need the difference of the y values. So we'll have f of 1 minus 1, that's the y value on our curve. That's what we'll get when we plug in 1 there, minus the y value of our point. So on the bottom, well, actually, let me do it this way. Have f of x minus 1. Sorry. So we're taking the limit. That's where we're starting. All we're doing there, let me go back. All we're doing there is we're taking this definition, f of x minus f of a over x minus a, and in this case we're plugging in 1 for a, that's the point that we're concerned with, our point P. 0.11, so x coordinate 1, y coordinate 1. Okay. So if we figure this limit out, it'll give us the slope of our tangent line at that point. So then what do we need to do? F of x, what's another way we can write it? F of x is equal to what? X squared. Another way we can write this is x squared minus 1 over x minus 1. And now we're just finding that limit. So forget about the rest of it. Okay, just focus on what we've been doing. We've been finding limits. Okay. If we are trying to find the limit of this thing, it's a rational function. If we try direct substitution on the bottom, what happens? If we try to plug in 1, we get 0 in the bottom, so that's not going to work. So then what are our other strategies? If we get a 0 in the denominator, what else can we do? We can rewrite our limit. I've got a couple of things. What's one? Yeah, we can factor. We can factor on this one. On top, we have difference of 2 squares. Difference of 2 squares. So if direct substitution fails, then try to factor. On the top, x plus 1, x times x minus 1. X minus 1. And then the x minus 1 terms cancel. So our limit here, we can do direct substitution now. Limit here is just 1 plus 1 or... Okay, so what is that? The slope of our tangent line at the point 1, 1 is 2. And then the thing we want, okay, we want to go one more step here. The thing we want, if we look back at the problem, we want the equation of the tangent line at the point 1, 1. So we've got the first piece of that, we've got the slope. So the other thing we'll need point slope form. So there's our slope, and then the point we care about on this one, point P is 1, 1. So we can use our slope of 2, our point 1, 1. What do we get here? We get y minus the y coordinate of our points, 1, equals the slope that we just figured out using that limit, 2, times the x coordinate of our point, the x minus the x coordinate of our point, which is 1. And there is an equation of our line. Okay, WebAssign will take that in the point slope form. Okay. If we wanted to, we can go a little bit further, right? We could solve it for y. Get it in slope intercept form. So there, 2 times x, 2x, and then 2 times -1 is -2, and I'd have to add 1 to both sides. So y equals 2x minus 1, and we solved it for y. So really, WebAssign's fine with it right here, point slope form. If you want to solve it for y, not too much more work. The slope of our tangent line. And one thing we can do to check it, we can look at the graph. So let's check ourselves. If I can get it to load up on the slow Wi-Fi. Okay, so our graph was x squared. We said the tangent line to the point 1, 1 should be 2x minus 1. We're trying to get the tangent line at the point 1, 1. It looks pretty good. Looks like we hit it where we wanted to. Yep. Yes, yeah, that's all it is. Yeah. Yeah, good question. Yeah, f of a, we just take whatever the a value is, okay, which is the x coordinate of the point that we're dealing with, plug it into the function. So what happens if we pick a different point? So maybe we want to know about 0.24. That would be on x squared. We're going to get a different tangent line. We'll have a different slope even, and we'll have a completely different tangent line. So using this definition, what we would have to do if we wanted slope of the tangent line at some other point, then we would have to go through, find the limit again, get the slope, plug it in, we'll have a whole new tangent line, whole new slope. So questions on doing one like that? Something you might have kind of noticed. So let me put our point on here so we can see where it's at easy too. There's our point where our line is tangent to our curve. If we zoom in, so we've got the red curve is x squared. The blue line is our tangent line. So if you just look in the area around our point 1, 1, you notice anything about the graphs? Let's zoom in some more. Zoom in some more. The red line's x squared, the blue line's our tangent line. What's going on when we zoom in around our point where it's tangent? They're practically, what's the difference between the two graphs? Practically nothing, right? They're practically on top of each other. So if we zoom in enough, something kind of interesting with the tangent line and with the curve, that if we zoom in enough locally, we could say they're basically the same graph. Something to keep in mind there. That'll be come into play. If we zoom out, we can see the difference, right? Because the tangent line only matches up with the red graph when we're really close around the point 1, 1. Do zoom in, they're basically identical. That's that one. And if we have an equation, have a function, then we can find the slope of the tangent line at some point using that limit definition. Let's So an alternative way of writing the same thing, just slightly different notation. So our denominator on the other definition was x minus a. If we take and let x minus a, we just give it a name and call it h. And if you solve for x, you get a plus h. So then we could write it this way: the slope of the secant line at the end would be f of a plus h minus f of a over h. So then in that case, if we wanted the slope of the tangent line, or we would have our limit as h approaches 0, and it's x minus a approaches 0, or as x approaches a, x approaches a, sorry. Okay, so that's our, that'd be in that notation, and that's the slope of our tangent line. So you'll see it written both ways. Where you think about the denominator going to 0, or you could have it where we have the x minus a on the bottom and talking about as x approaches a. It means the same thing. It means exactly the same thing. It's just two different ways to do the notation. So that's just a revisit of our finding the slope of a tangent line to a curve at some point. Now we've got all this limit stuff behind us, so we can finish writing that idea down and make it formal. So let's visit thinking about velocity. So we're doing the same thing. We're just interpreting this idea of slope of a tangent line with a physical quantity. We've already set this one up too, right? This was one of our motivations for coming up with this limiting idea. So we're delving off into physics a little bit. That's where calculus gets its roots. What it was developed for. It works on lots of other things, but it was developed for physics. So if we have a function that's giving us the motion of some object, sometimes you talk about a particle or something like that, then we would get the position function of that particle. So we're saying where's its location is compared to time. So here we're just thinking about position along a straight line. So our two axes, right, we'll have the position on the line versus time. It's a two-dimensional graph. So if we're thinking about its position between two different times, we can say we call one of them time A, and then time A plus a little bit, okay, plus h. So it gives us the actual time interval. Then we can find that position that way. Same that last definition we saw. We have f of a plus h minus f of a. Okay. So here's kind of a picture. So we've got one axis for location, and our other axis would be time. Okay, so the difference in position, and is where's it at time A, and then where's it at time A plus h. That. So then, remember what we talked about last time, we could get average velocity. Just take the distance we've traveled, the displacement, and divide it by the time. So here our time interval would just be h. A minus a plus h, or a plus h minus a, you just get h. And that all boils down, we've already seen it. I know it's kind of maybe a little boring. Okay, we've already seen it that it works out just like slope of the tangent line. Okay. So a way we can define instantaneous velocity, and not over a time period, but right at one instant in time. We can take and define that as this limit. We've seen several times. A plus h is, yeah, so, well, so we got to define two different ways, right? If we're thinking about, let me scroll back here. So you can think about it with this definition, right? Where we've got an x and we've got an a, and we're looking at our limit as x approaches a as the two values get close together. Or we got that second definition where we're just calling the x minus a part, that distance, we're calling it h. So then we've got the two y values. One would be f of a plus h, and another would be f of a. See the relationship there, kind of. And then that way we can just think about the denominator going to 0 instead of it approaching some number. That's like the top part's like the distance between our y values. And then the bottom parts, if you have 2, it's like the distance between the x values, or when you just have the h, you could say like the interval over which we're thinking about the change. Yeah, good question. So here what we're saying is we're going to let our time interval get smaller and smaller. We're going to take the limit as it approaches 0. And then we'll look at how the distance there will take that limit to get our velocity. So we could call that a velocity function. That's a function of our time a. Limit is the average velocity. Now let's work a problem from this point of view. We're doing the same thing in all these. We're just taking different points of view. All right, so I think we worked a similar one. It says, suppose that a ball is dropped from the upper observation deck of the CN tower. Seems like I remember the CN tower, 450 meters above the ground. What's the velocity of the ball after 5 seconds? How fast is the ball traveling when it hits the ground? Okay. So since we want the velocity first on part A, we want the velocity when t equals 5. That gets us set up to find our limit on this one. So we need another equation that we're not given here. So here's our position function. Yeah. Here's f of t. So using our definition we've got set up here, we'll take f of t plus some time interval h minus f of t, and then divided by our time interval. And we're going to find the limit as that time interval goes to 0. So we'll just, instead of writing this one down, we'll just walk through what we got in the slides. So f of t plus h, all that means is we take t plus h and plug it in where t is in our position function. All right, so we get 4.9 instead of times t, we get times t plus h squared. For f of t, we just get our function back. And then we got h on the bottom. Where the algebra gets messy on these is when we start having squares and cubes and things like that on our variable, because we have to FOIL that out, that t plus h squared. So if we do that, t times t is t squared, and then we got t times h times t. When we add those together, we get 2th. And h times h gives us h squared. Here what they've done is they've factored out the 4.9 here and here. to leave us at minus t squared on the end. Not absolutely necessary. Can do that. So then the big takeaway, okay, after we get all that mess simplified, what happens in there? We've got t squared and a minus t squared. Those cancel. And then this is what we get left with. And if we try to find this limit the way it's written at the end of the slide, what's the problem? Yeah, because if we try to plug in 0 for h, get 0 on the denominator. So can't do that. So then what other option do we have? We get in a situation where we try to find the limit of a rational function. If we get 0 in the bottom, then what else should we try? Try factoring, yeah. So it may not be jumping out to you, but part of that's because they've got that 4.9 factored out. So let's just look at this term and this term. That other 4.9 is just a constant, so we're not real worried about it. You see anything in common? H. Yeah, we've got an H in common. Okay, so what we can do is we can factor the H out. And so here's that H factored out. And then it will cancel with the 1 in the bottom. Just leave us with 4.9 times the 2t plus h. And then we can use direct substitution. We just plug in 0 for the h. So we just have to find 4.9 times 2t, 9.8t. And then on this particular one, it wanted the velocity at time 5, right? T equals 5. We just plug in the 5 for t. 9.8 times 5 gives us 49. Not too bad. The algebra on find the limit, right, is the part that can get messy. This one wasn't too bad. We had to FOIL a little bit, but it was not horrible. And then we had to see we had a common factor of h to factor out. Not too terribly bad on that. Yeah. Okay, let's look at part B on it. The B part says how fast is the ball traveling when it hits the ground. But on that one, thinking about that, if it hits the ground, how far has it traveled? That's important. It's gone 450 meters. 450 meters tall, where we're dropping it from. Okay. We've already got the position function, right? Sorry. 4.9 t squared position. So we can figure out the time when it's going to hit the ground, because its position after a certain amount of time has to be, it's traveled 450 meters down. So then we want the velocity after 9.6 seconds. That's when it's going to hit the ground. And then we're just adding on a little bit here. Right? We got 9.8t. That gives us our limit there. So plug in. It used the square root of 450 over 4.9 instead of 9.6. It's just using the exact answer there. That's all they're doing. Hanging in there. I know it's not super exciting because we've seen a lot of that already. Just kind of tying all the loose ends together. Not all that is. Okay. So, okay, two different problems, two similar solutions. Okay. That's what we're getting at here. Okay. That the slope of the tangent line solves both of these types of problems for us. Okay. So that leads us to our big topic. That is derivatives. So what in the world's a derivative? Okay. Big calculus topic. Okay. So in both of these cases, okay, with the slope of the tangent line, with instantaneous velocity, we've run across limits that look like this, okay, that we can write like this, or one of the other forms. And these types of limits pop up a lot. They pop up a lot. So anytime we're talking about a rate of change, then these type of limits come up. And so we got examples here. We've got, they're everywhere: engineering, chemistry, economics. Okay. Anytime we're talking about a rate of change of some variable, if our function is not a straight line, and we want to talk about rate of change, then we're going to get a limit that looks like this. A limit that looks like this. If we just have a straight line, it's easy because we just talk about slope. And slope is well defined for straight line. We've got all that handled. But lots of functions are not straight lines. So in order to talk about the rate of change of those, we get this kind of limit. Okay. So since this pops up so often, we give this kind of limit a name and a notation. So this limit, if we're talking about that limit of a function f, then we say this is the derivative of function f at a. And a is just some number. It will be some x value. And our short notation for derivative is we just take the function, whatever it is. Here we're working with f of a. I'm going to put a little tick mark with the f, like a single quote. Is this the derivative of our function? So anytime you see this thing with a tick mark, referring to this limit, referring to that limit. So the thing on the left, we could say it's the derivative of f at a. I'm getting a little bit ahead here, but another way you can read that is you could say f prime at a. That little tick mark you can think about as prime. Hear that phrasing? Mainly because it's a lot shorter to say f prime than it is to say the derivative of f. F prime's over there a lot. Okay, and then remember we had, instead of using h for our denominator, we could do x minus a, so you can equivalently define that thing that way, instead of throwing the h term in there. Okay. This one's kind of nice because it looks more like a slope, right, which is what it is, right? It's the limit of the slope of the secant line as we have 2 points getting closer to each other. And so that's nice. But in another sense, this one's nice because we can just think about the denominator going to 0 instead of two numbers getting close to each other. So they both have their advantages, both notations do. So that's the derivative. So let's look at another problem. Again, this is the same thing we've done. Same thing we've done. Let's look at it. So we want to find the derivative of this function at some number, and we're not even going to specify the number. We're just going to call it a. And so I'm just going to go over to scratch paper and we'll walk through what all that algebra is. If you're not very algebra comfortable, the algebra can kind of get overwhelming, so just take it one little step at a time. We want the derivative of f of x, and then here our function is x squared minus 8x plus 9 at this number we're just calling a. This x value we're just calling a. Okay. So we can use either definition. I think I'm going to use the one with the h in it. So this is what we're looking for, right? We're looking for the derivative of f at a. So our definition, if you use the one with the h, turn it like this, I want to say that it's the limit as h approaches 0 of f of a plus h minus f of a over definition. So now we just need to figure out what that top part's going to be based on our function. And our, it would be our x value, but we're calling our x value a. So what's that going to be? This is where it gets a little messy. It works out nice in the end. We just have to go through some mess to get there. So f of a plus h, that just means everywhere we had an x, we substitute it with a plus h. So we'll have, instead of x squared, we'll have a plus h squared minus 8 times a plus h plus 9 and we've got to do the same thing with f of a. It's easier, but we do have to be careful because we're subtracting here. So if you're doing one of these, I strongly recommend putting a parenthesis or a bracket or something there to remind you have to subtract everything that comes after that. That's going to flip all the signs. So here we'll have a squared minus 8a. All that's over h. So on both of those, I'm just taking, on the first one, I'm substituting a plus h in for x. And on the second one, I'm substituting a. So now is where the algebra gets a little tedious. So we gotta work on this thing. Because right now, if we try to do direct substitution, we're in trouble because in the bottom we'll get 0. We got to rewrite this thing so that doesn't happen. The way we can get started on that is we can simplify the top. Simplifying the top, we've got some algebra involved there. So a plus h squared, if you FOIL that out, that's a plus 2ah plus h squared after you combine like terms. Then we've got distributive property, so minus 8a minus 8h plus 9. And then we're subtracting everything that comes after the minus sign here. So we can switch all those signs. So minus a squared plus 8a minus 9h. So big mess there. But it's kind of a nice mess because we get some payoff for doing all that. We get some cancellations. What, you notice anything canceling? Yeah, we got a squared minus a squared. Okay. Yeah. What else? Plus 9 minus 9. Yeah, plus 9 minus 9. We got one more term. Oh, yeah, minus 8a plus 8a. Hey, so we get rid of a lot of that. It cancels out. So then the limit we're trying to find gets easier. Thank goodness. So let's see, I'm going to put the h squared first, just because we normally put the bigger exponent first, and then got plus 2ah. And then the only other thing I have left is minus 8h over h. Sadly, we're still in a situation where if we try to find the limit, direct substitution is not going to work because of our denominator. So then factor out an h. Yeah, factor out an h. So you'll see a pattern. Okay, anytime you're doing these, using this definition of a derivative, you should have a common factor of h left in the top, so you can cancel with the one in the bottom. So on the top, if we factor out an h, this with h plus 2a minus 8 over h. H's cancel. And then now finally, what can we do to find our limit? Yeah, we can substitute in for h. And it's going to be weird. We're not going to get an exact number out because remember our x value we're calling a. So this limit will depend on our x value. So when we plug in, we'll have 0. We're going to plug in for h plus 2a minus 8. So we just get 2a minus 8. So we would get a different limit depending on what a value we were using. That is our derivative. This is f prime at a. Derivative of f at x equals a. Okay. This is messy. We get it. Okay. Oh, that's so. Okay. So that's where we ended up, right? 2a minus a. Okay. So here's another thing we can reword. We figured out about the tangent line to some curve f of x. And it goes through some point P. And then we figured out that limit, okay, the slope of the tangent line is the same thing we're calling f prime of a now, the derivative of f at a. So if we want to talk about an equation of a tangent line in this situation, now we can write that a little more simply. And we can write it like this. So here was how we were writing it down before. We were saying this is y minus the y-coordinate of the point where we're tangent. We said that equaled the slope of our tangent line, which now we can call f prime of a times x minus the x-coordinate of the point where we want our tangent line. So now instead of writing all that and then going through finding the limit, we can call it what it is. Okay, we can call the slope of our tangent line at point A, let f prime of a. That nice little looking equation there. Not much more lecture here. We're going to do a couple more examples, but not much more lectures. Hang in there, hang in there. Know when we're saying the same thing over and over, it's not great. In general, if we're just thinking about rates of change, we can use the derivative idea. Use this idea of this specific type of limit. So anytime we're talking about the rate of change, we can use that. So let's kind of make it generic here. We've got y that we can express as a function of x, because it depends on the quantity x. So we can say y equals f of x. And our x component, whatever that is going to change from x1 to x2. So we're looking at two different x values. Then another way we can write that, okay, saying the difference between the two x values, we can write that as delta x. Seen that before? In the delta notation to represent a change. Maybe some of you have. And so if you see delta some variable, lots of times we use that to represent the change in that particular value, okay, or that variable, I mean. So that's like the change in x. The way we would calculate that's x2 minus x1. And then the change we would get in y, we just find the difference between our two y values. So in that case, that part's f of x2 minus f of x1. How much does that change? So then when we think about slope between those 2 points, remember our slopes rise over run, right? Change in y over the change in x. So another way we can write that is delta y over delta x. How much do our y values change as a ratio of how much our x values change? So then this limit, okay, we could write this way. So this, right, delta y over delta x, that's our average rate of change, okay, over the interval x1 to x2, however far that is. So instantaneous, okay, we can talk about this limit as our change in x, or delta x, approaches 0. We get instantaneous rate of change. And all it is the same limit we've been talking about. And because of that, I think that just means it's just the derivative. Okay, so another way we can write that limit definition. And you will see that sometimes it's written like that. The limit is delta x approaches 0. Sometimes you actually see kind of these two versions combined. And this is actually the way I learned it the first time I learned it. Which is it's kind of funny, I even remember that. Okay, you'll see it like this, but then on the top, we could write it x plus delta x like we did with the h. Over delta x. That's kind of a in between the two. So derivative. Here, the derivative would be instantaneous rate of change. So let's think about one. Yeah, we got all that. So, okay, let's look at this. last example here, and then we'll work some like the homework problems. Some more like the homework problems. We've done a couple that are simple. This is not a long assignment. I think I gave you 6 problems because they take a little bit of time, and if you make a mistake, you have to go back and find the mistake and all that. So didn't try not to overwhelm you. So let's look at this one. Okay, it says a manufacturer produces bolts of a fabric with a fixed width. Cost of producing X yards of this fabric is C, which we've got a function for C, f of X, dollars. Okay. So part A, we want to know what's the meaning of the derivative. What's our interpretation of the derivative there, and what are the units? Okay. Units. So how can we start thinking about that? So f of X, or C, if we want to think about it that way, that's like our y's. So what we would be thinking about is we'd be thinking about how C changes, or how f of X changes, compared to how X changes. Okay. And we would want that limit delta X approaches 0. That would be our derivative. One way to write the derivative in this case. So first, let's think about the units. So we can think about the units at the top and the units at the bottom to figure that out. So C, what units are our C values in? It says C is f of X dollars. So we'll have dollars on the top. And then X, what units are X's in? Yards, X yards. So our derivative here will be dollars per yard. Dollars per yard. Well, yeah, dollars. That would be our units. Because the top's in dollars, bottom's in yards, so dollars per yard. And then C is our cost function. So we're talking about how our cost function changes based on how the yards of fabric we're producing changes. So what's our interpretation on that? We're talking about how the cost of production changes based on how many yards of fabric we're producing. I don't have a good name for that, okay, but that's what the function is. Talking about how our cost of production changes versus how many yards of fabric we're producing. So there you're kind of talking about things like economy of scale, if you've heard that phrasing before. Right? Like how does it change our cost of production if we're making 5,000 yards of this fabric versus if we're making 2 yards of the fabric? Sometimes it would be more expensive per yard to make 2 yards than it would be to make 5,000 yards. That kind of thing. All right, B says in practical terms, what does it mean to say that f prime of 1,000 equals 9? So here's f prime, our derivative. So what's it mean if our derivative at 1,000 yards of fabric equals 9? Think our way through that. So first of all, is 9 positive or negative? It's positive, so that means something's going up. Okay, something's increasing because it's positive. And our derivative is like the rate of change. So what's increasing at 1,000? Our cost of production is increasing by $9 per yard at the point where we're making 1,000 yards of fabric. We don't have a lot of context for that. That's our interpretation. So at the instant where we're making 1,000 yards of fabric, our cost of production is increasing by $9 per yard. Okay? So maybe when we get to like x equals 50,000, where we're making 50,000 yards, maybe our cost of production would be going down. Okay? We don't know. We don't have all the information. We don't have the whole equation there. Okay? But that would be our interpretation. Sometimes it's kind of hard to interpret that with no context, but that's what it's saying. So we're saying at the point in time where we're making 1,000 yards of fabric, our cost of production is increasing by 9. That's the slope of our tangent line. It has a positive slope of 9. And then our units there, we figured out on the last one, is dollars per yard. So for some reason, when we're making 1,000 yards of fabric, it's making our cost of production go up. Okay. So let's just bang out a couple of these using the definition to find the derivative, and then we'll be done. Want to give you plenty of examples so you don't feel like you're out, in the middle of nowhere trying to figure out how to work these. We've done a couple, right? We've done a couple, but do some more so we get a little more comfortable. Okay. And I'll try and pick the nastier ones as far as the algebra goes. Okay. These are not my favorite to work either because they're tedious. Okay. The good news, here's the good news. I'll give you a preview. And it's not in chapter 2. We've got one more section in chapter 2. So when we get to chapter 3, we're still going to be finding derivatives. But the good news is we're going to have a better way of finding these than having to use this definition. Okay, so we're not going to be stuck using this definition. Okay? For right now, that's how we're finding derivatives. Turns out there are some more elegant ways to. There's a preview. Give you a little hope. Okay? So let's look at this one. We want to find the tangent line. We want the whole equation of the tangent line. Maybe we'll just do this one. Curve. Here's our equation. X cubed minus 2x plus 1 at 0.322. So I only gave you 6, but I was a little meaner than I thought because we've got 3 of them that have a cube involved. Here we go. Our definition says if we want derivative, what value are we finding the derivative at on this one? What would be our A? 3. Okay. This is our point, is A, f of A on our definition. Okay. So we want the derivative at x equals 3 of this thing. So that is the limit. H approaches 0 of what we got, f of A plus H minus f of A over H. So we can think about it that way for now. 3. This we'll save this till the end. Or should we? Let's see. Yeah, we'll just save it to the end. You can try to use it now for A, or you can wait to the end, either way. This one's a little messy, so I'm just going to wait to the end. So, what are we going to get here? So we're going to have, for f of a plus h, that's a plus h cubed, sorry about that, minus 2 times a plus h plus 1 minus big bracket, well, f of a will have a cubed minus 2a plus 1 all over h. If you remember the shortcut for cubing a binomial, it helps. If not, a plus h cubed, you could do a plus h times a plus h times a plus h. So FOIL 2 of them and then multiply by a plus h again. And here's a shortcut. Using that Pascal's triangle we mentioned way back. Well, so let's just might as well. That's the one we need there. Yeah. So if we'll get the coefficients, our coefficients on our new polynomial will be 1, 3, 3, 1. So this is the binomial squared, binomial cubed coefficients. So what are we going to end up with? We're going to end up with a cubed plus 3 something. And the something will be a squared h. And you go down 1 on the a, up 1 on the h. Plus 3 again. Down 1 on the a, so a. Up 1 on the h squared. And then 1 is our coefficient on the last one, and that's h cubed. There's that, and then we've got distributive property minus 2a minus 2h plus 1. And right in here, you kind of start hating the math teacher. It's all right. Then we distribute the minus sign on our other one, so minus a to the third plus 2a minus 1, all that mess over h. And then you really hope some stuff cancels out. Well, you see that cancels. Yeah, plus 1 minus 1. Yeah, that's out of there. A cubed minus a cubed, that's out of there. Minus 2a plus 2a, that's out of there. Okay. Everything we have left has an h in it, so that's good. So that means we'll be able to find our limit by factoring an h out. So where are we at? We're here, so I've got an h cubed, 3a squared h, 3ah squared, and a minus 2h. That's everything, 4 terms, right? Over h. We factor an h out and cancel it. I'll forgive you if you don't write that step down at this point. And you end up with h squared plus 3a squared plus 3ah minus 2. So factor out and cancel an h. We plug in for h0, do direct substitution. What's that going to leave us with? H squared is 0. And we got 3a squared. 3ah. What happens on that one? 0, yeah. I get minus 2. Okay. And then we could have done this at the beginning. We could have dealt with a bunch of numbers in there instead of a's, but what else do we know? We know a is 3. So plug in for a. What do we get there? 25. Okay. This is the slope of our tangent line at 3. Okay. Almost finished. The hard part's over. Okay. The other thing we need is our point. 322. So now we can plug into this. So y minus our y coordinate equals our slope times x minus our x. WebAssign will take that. Want to, you can solve it for y. So let's see, 25x minus 75 plus 22. Negative 75 plus 20. Either one of those. Let me make sure. Let me see if I got this. Yeah. Okay. Ooh. Questions on doing them? They can get a little ugly. The algebra can get a little ugly, but remember, keep the good news in mind. Keep the good news in mind. We're not going to have to do them this way forever. We're not going to have to do them this way forever. And also, a cube is the worst I gave you. I didn't give you didn't give you anything with x to the 5th or anything like that in there. Okay. And there's only 6 problems, so there's only 6 problems. Okay, they're bad enough. The goal to me as the teacher is to make it miserable enough that you're really happy when you don't have to do it anymore without just making you mad for no reason. So that's the goal. Okay. All right, that's it for this section. If you didn't sign the sign-in sheet, make sure you get it on your way out.